Okay, I'm going to get started. Today I'm going to talk about consumption smoothing. Answer some questions that came up and that continue to come up, and talk about something called precautionary savings. And there's going to be a tension between the Friedman-Hall linear quadratic permanent income model and one in which we abandon the quadratic utility function and use one that's more like we've used in chapter 9 and other places. So I'm going to go back to basically chapter 3 of RMT 5 for a few minutes, and actually I'm going to be talking about pages pages 104, let's see, and 105, and there's a footnote on page 105. Okay, so I'm just going to go fast and just remind you what the setup there was. The setup was we had a single consumer. Consumer had a sequence of budget constraints that looked like this, where BT was risk-free debt that is due at time t. CT is consumption. YT is an endowment process. YT was a stochastic endowment process, which we modeled as a function of a Markov state. We imposed arbitrarily, I imposed this restriction on the amount of debt. I just imposed this from outside in order to make the problem have the answer that Friedman and Hall got. And if I didn't impose this or something like it, the answer would have been different. So this, in addition, we imposed that R times beta was equal to 1 following Hall and Friedman. Classic things. And we had a consumer that cared about the following: ranked plans according to this utility function, where UT, where U of C satisfied the properties that U prime was positive and U neg prime was negative. And to get to the Hall-Friedman model, we assumed that U prime of C was some linear function, that it was affine in C. So this was some bliss level of consumption, and we just had a quadratic, basically U was quadratic. Let's see where we use that. So this was the general thing we imposed, and this was the special thing. So linear or affine marginal utility. I'm actually talking about this because a couple of you asked me a question to explain quote unquote intuition for the random walk result that Hall got. And I'm not sure I'm going to be able to tell you intuition, but I'll tell you we'll just review the math. So here's a small digression that underlies this. The source, the motive for consumption smoothing. This underlies the logic of this model and many of the models we've talked about. So our utility function looks like this. Here's C, here's U of C. And it looks like this. It's this. So if we take a 2 points here, C low, and we take a point C high up here, and we ask the person, would you like to be 50% of the time here and 50% of the time here? Well, if that was true, how much would your expected utility be? It would be, connect these with a straight line. If you got 50% here and 50% here, your expected utility would be right in the middle. It would be this amount. So that's expected utility of C. If you have to have this randomness, well, you would rather be in the middle and have no risk. So you would rather have the average all the time than be half the time here and half the time here, because you'd rather be here. So that's the source of the U prime being negative is the source, the motive for consumption smoothing. If we make the utility function linear, that motive goes away. So this is all about the concavity of the utility function. So this person wants to smooth consumption across time and across states. Okay, that's a digression. And that's true with either one of these in general. Okay. So that, by the way, is a motive for smoothing any concave utility function. And Barrow saw that if he reinterpreted what people cared about, in particular a government that cared about distortions that come from taxes, very similar logic that to what Hall had would allow him to produce a model of optimal tax smoothing. Something that we've seen. Okay, so let's go return to the consumption problem, return to the problem, and we'll get the first order necessary conditions, the so-called Euler equations. And among the first order conditions is this Euler equation for consumption. So if you do that, and you saw this before. So there's the condition for all t greater than or equal to 0. That condition comes out of this problem, where the person wants to maximize this over consumption plan subject to this sequence of constraints. So that's what we got. So what this tells you is where that's the conditional expectation of the margin utility consumption tomorrow, conditional on information today. Okay? So this tells you that the marginal utility of consumption is a random walk. It's a martingale. Or a martingale. And so we just stare at that. So it didn't tell us consumption was a random walk. It told us that the marginal utility of consumption is a random walk. But so what Hall said, and what Friedman implicitly had in mind was, well, if U prime of CT is just B minus CT, then consumption is a random walk. So if I have a linear marginal utility of consumption, affine marginal utility of consumption, this immediately implies that consumption is also a random walk. Okay. But now let's go to the more general case. And this is going to be the subject of footnote 5 on page 105. So we're going to talk about it. We're going to stare at that footnote. It's very short. Okay. So what I'm going to do is I'm going to modify, or I'm going to, I would say, I'm going to amplify what we assume about the utility function. And I am now going to assume that U prime is positive, that this is double prime is negative, and I'm going to assume that U triple prime is positive. And this rules out affine marginal utility. And in particular, I'm now going to assume, we're in a business of doing if then, that the marginal utility is going to look like this. I'm going to have U prime of C, and I want the marginal utility of consumption to look like this. I want U prime always to be positive for all C. I want that, and I want that, and I want this condition. So I'm going to have a positive third derivative of the utility function. So I'm now going to impose that. This is stronger. This condition is stronger than much of what I'm going to impose today. For most of today's exploration, I won't impose this positive third derivative. But in a way, following some giants, I'll impose something like it. Okay. Okay, so I'm temporarily imposing this. So we're temporarily, for the purpose of this, I'm going to impose U triple prime is positive. So now I'm going to remind you what's in this footnote 5. So we remember we have our Euler equation. What's our Euler equation? Our first order condition. This is just a reminder. It's the conditional expectation of the marginal utility consumption. This is our first order condition. This is depending on beta R equals 1, as Hall assumed. So that's our Euler equation. And now I'm going to apply Jensen's inequality. Well, Jensen's inequality with the third derivative condition that I cited earlier, implies that u ct plus 1 is strictly greater than u prime et ct plus 1. And this, I'm just going to say this in a way is just a version of this picture, except in what I have on my axes here aren't going to be utilities, they're going to be marginal utilities. So it's up a derivative. So this is Jensen's inequality. So I'm going to say draw a picture or look up Wikipedia. Okay, so now I'm going to combine these two equations. There's my Euler equation, and there's this. So what these two equations imply now is that ET, something remarkable is going to happen. Is now greater than u prime et ct plus 1. But what that means is that u prime let me just pause here for a second. Okay. So let's just string these together. So these imply that, oops. Sorry. These imply